Here's an old favorite. This is the motor. Looks a lot like a generator, and generally tend to find that in 0654 they include one of those generators or motors in our papers. This time it's a motor, sorry, and so we're going to try and have a look at what's going on here. As ever, please try the question. Make sure you've sort of got an idea of what this question is before having a look at my answers. Okay, so we're asked here about the motor. All right, nice starter question for 3 marks here. We're being asked, we've got a current carrying coil in a magnetic field, and we want to know how we can increase the turning effect. How can we make it rotate faster? Well, let's give you an example of the kind of answer that we're looking at here. We're looking here, for example, increase the current. If we change the current, then it will go faster. All right, if we increase it. Now notice I've got to be a bit careful here with my language. Firstly, do not say what I've just said there, change. You say increased. Okay, increase the current. Don't just change it, increase it. Because change is too vague, it implies perhaps decreasing. If you decrease it, it will decrease the rate. So you're looking for that. Some students here will tell me how to change the current. So they might say, add another cell. That's a lovely answer. You could think of decreasing the resistance. That's too much, too good an answer, if anything. You're really giving too much detail, right? That's describing how we would do that. Here we just want to state it. So a nice 3 marker. All right, increase the current. We're going to also increase the field strength, okay, by perhaps adding another magnet, by bringing the magnets close together. We don't need to express how. And the last one, increase the number of turns. We've got more wires, more forces. So it's a nice start there. 3 marks, right? Remember here, your physics section is 40 marks. That is 3 out of 40. Trying desperately to do that maths in my head. 7.5% of your physics marks done just by writing down 3 things we could do to increase the rate of rotation. We're then asked about this component X. I'm deliberately not showing the answer there because if you don't know the name of X, quickly have a think, go and find it out. I'll reveal it in 3, 2, 1. This is the split ring commutator. Okay, emphasis here on the full name, split ring commutator. I've seen various answers in the mark schemes. They insist on seeing split ring. Okay, sometimes they insist on commutator, and this year they wanted the whole thing. Reason being here is there's something else called slip rings. Slip rings are for generators. Okay, so if you are talking about slip rings, you're talking about generator. In this case, we're talking about the split ring. You can see that there's a big similarity between those 2 words, split and slip. Okay, you must make sure you write the right thing here. It's one of the few occasions where they will not allow you to kind of make a typo as you're writing down. You've got to make sure you write down the right thing there. Okay, we're then asked how component X, the split ring commutator, is used to allow continuous rotation of the coil. And again, I've deliberately hidden this because this is a standard question and it's one which has a really standard answer. So if you know it, try it. If you don't know it, okay, find it out and then have a look at what I've written down. Okay, key point here is that our split ring commutator allows the circuit to break, all right? And as a result of breaking, the commutator reverses the current. It changes the direction of the current. It does that every half turn to maintain constant rotation direction. Now, again, my answer may not quite hit the points on the mark scheme every time. However, one thing that I've noticed is that this question comes up, but it has sort of different points in the mark schemes, and this is the most consistent answer I can come up with. Generally, they're looking for the idea of reversing the current direction. We are changing the current direction. Okay, and we're doing that every half turn. This is the most reliable, quick, snappy answer that I can come up with, which will allow you to get the full marks here. All right, I'll be honest with you, I don't think many students fully understand what is going on inside here. However, you do not need to. That's the surface level we need to go to. It's the idea of reversing the current direction every half turn, hopefully 2 marks there. All right, let's go down a little bit further. Okay, we're in the electromagnetism part of the topic, so we're going to then start talking about, of course, transformers. Okay, we're asked firstly, what type of transformer is used at power stations to supply power to the electricity network, aka the electrical grid? Now, this is using a step-up transformer, and again, it's one of these things that you could just remember, or we could talk about why, and that's what we're going to do below. So just to know that if you are going from the power station to the grid or to the network, you are stepping up. If it's our homes, I'm sorry you can't see this clearly here. All right, let me just move this over. There you go. In our homes, we step down. So what happens, just to be clear, we've got power station, step up, electricity network, wires, cables, pylons, whatever you want to call them, to our homes where it's stepped down. It might be stepped down a couple of times, okay, which is then safe for us to use in our homes. Okay, so you've got step up and then step down. We do not step up and then leave it like that. That would be very dangerous. The reason we do this is because higher potential will reduce the current. Okay, we assume that there is 100% efficiency in our transformer. Now the result of that, and again, this is something you can remember or you can work out yourself, up to you. Yeah, the higher the potential, the lower the current. If we have a higher potential, lower current, we reduce the power loss in our wires. Okay, so again, you notice here, 3 marks for a relatively kind of nice question. Higher potential reduces the current, power loss is proportional to I squared, so therefore lower I, lower power loss. Okay. All right, last one. Yeah, we've got a nice calculation question. Again, really common question in terms of calculations. All right, we've got a transformer connected to a 230 volt main supply. That's VP. Okay, we've got an output 3.6. That's VS. And you notice here we're going from high to low, so it's step down. Okay, we're then told the secondary coil NS has 720. So we want to know NP, the number of turns on the primary coil. We're going to use this one. A little bit worried about this equation. I know students hate it because there's lots of there's 4 symbols, and generally when you get to 4 symbols, we don't like them, right? The way to remember this is, firstly, I would write it down in this way. Okay, keep the N's on the same side and the V's on the same side. Okay, so N over N, V over V, and an equal sign in the middle. Now, what goes on the top and the bottom? Well, then see the subscripts, for example, P and P, S and S, those match. So NP over NS equals VP over VS. I've got NP, VP, NS, VS. Okay, that is going to allow you to manage to do this one. Okay, all right, all we're going to do after that is rearrange our equation, put in our numbers, okay, and we're going to end up with our answer here, 46,000. Now, if you compare that here, we've said 46,000 in the initial coil. We started with, and then we've got 720 on the final, so that is definitely a step down, which is why our answer here is so big.